you can refer to the table and reuse previously calculated distances, avoiding redundant calculations.
So it's like having a map with all the best routes already highlighted, saving you tons of time and effort.
Exactly.
It sounds like dynamic programming and recursion are all about optimizing performance.
Right.
But how do we actually measure and compare the efficiency of different algorithms?
That's where our old friend Big O notation comes back into play. Remember, it's all about understanding how an algorithm's performance scales as the input size grows, focusing on the overall trend rather than precise measurements.
Right, it's like comparing the fuel efficiency of different cars.
Yeah.
You're not concerned with the exact mileage for every trip, but with the overall gas consumption as you drive further.
That's a perfect analogy.
Yeah.
And Cormen emphasizes that understanding Big O notation is crucial for making informed decisions about which algorithm to use for a given task.
Yeah?
An algorithm that works fine for a small data set might become terribly slow as the data grows.
The Big O notation is like a crystal ball, helping us predict how an algorithm will perform in the long run. It's about choosing the right tool for the job, based on the size and complexity of the data we're dealing with. Now, up until now, we've talked about algorithms in a somewhat abstract way, like recipes for solving problems.
Right.
But what about the ingredients themselves? How is data actually organized and stored within a computer?
That's where data structures come in. They are the building blocks of the digital world, the containers that hold our information in a way that allows us to access and manipulate it efficiently.
So data structures are like the shelves, drawers, and filing cabinets of the digital world.
Precisely.
Okay.
And just as there are different types of containers for storing physical objects, there are different types of data structures for storing different kinds of data.
Okay, give us a tour of some of these digital storage solutions.
Okay.
What are some of the most common data structures?
One of the most fundamental is the array.
Okay.
Think of it like a row of numbered boxes, each holding a piece of data. Arrays are great for storing ordered lists of items, like the numbers in a spreadsheet or the characters in a text document.
So an array is like a digital filing cabinet, with each drawer is labeled for easy access.
Yeah.
What other data structures are out there?
Then we have linked lists, which are like chains of nodes. Each node contains a piece of data and a pointer to the next node in the chain. Linked lists are more flexible than arrays. You can easily insert or remove elements from anywhere in the list without having to shift everything around.
So a linked list is like a conga line, where each person is holding on to the person in front of them, and you can easily join or leave the line at any point.
That's a fun way to visualize it.
Yeah.
And there are many other data structures, each with its own strengths and weaknesses. We have stacks, which are like piles of plates where you can only add or remove from the top. Queues, which are like lines at a store where the first person in line is the first one served.
Right.
And then there are trees and graphs, which we've already touched upon in the context of shortest path.
It's like a whole ecosystem of digital containers, each designed for a specific purpose. And I bet choosing the right data structure is crucial for building efficient algorithms.
Absolutely. The data structure you choose can have a huge impact on how efficiently your algorithm can access and process the data.
So it's about understanding the strengths and weaknesses of each data structure, knowing when to use an array versus a linked list, for example. It's like a carpenter choosing the right wood for a particular project.
Precisely.
Yeah.
And speaking of choosing the right tools, let's dive into a concept that's fundamental to understanding how data is manipulated at a deeper level. Pointers.
Ooh, pointers.
Yeah.
They sound a bit pointy and dangerous.
Yeah.
Like something you wouldn't want to handle without gloves.
They can be tricky if you're not careful, but they're essential for understanding how computers work at a fundamental level.
All right, demystify pointers for us. What exactly are they?
In essence, a pointer is a variable that stores the memory address of another variable.
A memory address. Is that like a street address for a piece of data?
You got it. Every piece of data stored in a computer's memory has a unique address, and a pointer allows you to directly access that data by its address.
So it's like having a direct line to that piece of data, bypassing all the usual channels.
Exactly. And pointers are crucial for implementing linked lists, trees, and other complex data structures. They allow you to create connections between different pieces of data, to build up intricate networks of information.
Pointers, they're like the glue that holds the digital world together.
A very apt analogy.
Yeah.
And understanding pointers is essential for writing efficient and powerful algorithms.
Well, we've certainly journeyed deep into the algorithmic rabbit hole today, exploring recursion, dynamic programming, Big O notation, data structures, and even those tricky pointers.
We've uncovered some of the key tools and techniques that computer scientists use to solve problems and optimize performance.
But our adventure isn't over yet. Join us for part 3, where we'll venture into even more fascinating territory, exploring graph algorithms, string matching, and maybe even touch upon the profound implications of computational complexity.
The journey continues.
Welcome back, algorithm adventurers, to the final part of our deep dive into algorithms unlocked.
Very exciting.
I feel like we've covered so much ground already.
Yeah, we have.
But there's still more to explore.
Right. Or
Right.
absolutely. The beauty of this field is there's always more to discover.
Okay, so in this final part,
Yeah.
we're going to be exploring the power of graph algorithms.
Yes.
We're going to try and unravel the mysteries of string matching
Okay.
and maybe even touch upon the philosophical implications of computational complexity.
Sounds like a plan.
Let's get started.
Okay, let's start with graph algorithms. We've already encountered graphs in the context of shortest paths,
All right.
but they have applications far beyond navigation.
Right, like we talked about how graphs can represent all sorts of relationships, like connections between people on a social network or links between web pages, dependencies between tasks in a project. It's like they capture the underlying structure of so many complex systems.
Exactly. And graph algorithms provide us with powerful tools for analyzing and manipulating those relationships. One classic example is depth-first search, which is like exploring a maze. You start at a particular node and keep going deeper and deeper until you reach a dead end, then you backtrack and try another path.
So it's like a systematic way of exploring every nook and cranny of the graph, making sure you don't miss any hidden connections. What other graph traversing techniques are there?
Another common approach is breadth-first search, which explores the graph layer by layer.
Okay.
You start at a node, visit all its immediate neighbors, then visit all their neighbors, and so on. It's like expanding outward in concentric circles.
So depth-first search is like a spelunker, delving deep into the caves, while breadth-first search is like a surveyor, mapping out the terrain systematically. I like that.
Wonderful analogies. And these search algorithms are just the tip of the iceberg when it comes to graph algorithms.
Right.
There are algorithms for finding shortest paths, for identifying cycles, for determining connected components, for finding minimum spanning trees, a whole toolbox for graph manipulation.
It's like having a Swiss Army knife for graphs.
Yes.
So with all these powerful graph algorithms at our disposal, what kind of real-world problems can we solve?
Well, as we've already seen, shortest path algorithms are essential for navigation systems. But graph algorithms are also crucial for social network analysis. Understanding the connections between people and the flow of information through those networks, they can help us identify influencers, predict trends, and even understand the spread of diseases.
It's like being able to see the invisible threads that connect us all, those patterns that emerge from complex interactions.
Exactly. And graph algorithms are also used in fields like bioinformatics,
Right.
where they can help analyze protein interactions or map out genetic relationships. They're used in transportation networks to optimize logistics and routing. They're even used in artificial intelligence to model knowledge and reasoning.
It's amazing to think that these abstract mathematical structures have such a profound impact on our understanding of the world and our ability to solve real-world problems. Now let's switch gears and talk about a topic that's closely related to graphs. String matching. So we've already encountered strings in the context of text manipulation, but there's a whole world of algorithms dedicated to finding patterns within strings.
String matching is essential for everything from searching for information on the web to analyzing DNA sequences. One classic algorithm is the Knuth-Morse-Pratt algorithm, which efficiently finds occurrences of a pattern within a larger text.
So it's like having a superpowered search function that can instantly pinpoint the exact location of a specific sequence of characters within a vast sea of text. I like that.
Precisely. And then there are algorithms like the Boyer-Moore algorithm, which uses some clever tricks to skip ahead in the text, making the search even faster.
It's like having a speed-reading superpower for text analysis. Now, I remember we talked about finite automata earlier in the context of string algorithms.
Yeah.
How do they fit into this picture?
Finite automata are essentially pattern-matching machines. They can be designed to recognize specific patterns within a string, and they're used in all sorts of applications, from spell checkers to lexical analyzers and compilers.
So they're like tiny little robots that scan through text looking for specific sequences of characters.
Good way to think about it.
Yeah.
And the beauty of finite automata is that they're relatively simple to implement, yet incredibly powerful in their ability to recognize patterns.
It's a testament to the elegance of algorithmic thinking, finding simple solutions to complex problems. Now, as we wrap up our deep dive into Algorithms Unlocked, I want to touch upon a topic that underpins the very foundations of computer science, computational complexity.
Okay,
It's a topic that can get quite deep, but I'm hoping you can give us a high-level overview.
sure. Computational complexity is all about understanding the inherent difficulty of solving computational problems. We want to know how the resources required to solve a problem, time, memory, processing power scale, with the size of the input.
So it's like classifying problems based on how much um, computational effort they require.
Exactly. And one of the most fundamental insights in computational complexity is the distinction between problems that can be solved in polynomial time, those in the class P, and problems that are believed to require exponential time, those in the class NP.
Right, and those NP-complete problems we talked about earlier, those are the ones that seem to defy efficient uh, polynomial time solutions.
Precisely. And the question of whether P equals NP, whether every problem whose solution can be easily verified can also be easily solved, is one of the biggest unsolved mysteries in computer science.
It's a question that has far-reaching implications for everything from cryptography to artificial intelligence to the very nature of computation itself. It makes you realize that even in this digital age, there are still profound mysteries waiting to be unraveled.
It does, and that's what makes the study of algorithms so fascinating. It's a field that's constantly evolving with new discoveries and innovations emerging all the time.
Well, I think it's safe to say that our deep dive into Algorithms Unlocked has been a resounding success. We've explored a vast landscape of algorithmic concepts, from the fundamental building blocks of sorting and searching to the mind-bending challenges of NP-completeness. We've encountered elegant algorithms like Dijkstra's shortest path algorithm and powerful data structures like graphs and finite automata. We've learned about the importance of efficiency, the power of recursion, and the beauty of dynamic programming. And most importantly, I think we've gained a deeper appreciation for the profound impact that algorithms have on our lives. They're the hidden engines that drive our digital world, shaping everything from the way we communicate to the way we do business to the way we understand the universe itself. So, to our listeners, we encourage you to continue exploring this fascinating field. There are countless resources available online, and Cormen's Algorithms Unlocked is a fantastic starting point. Until next time, keep those algorithms humming.